All right, so chlorination versus bromination. This is something that's really important for the radical reactions. And before we go over, I just kind of want to do a brief overview. So remember we did chlorination of propane, and we obviously had the presence of light or heat, and we formed two different constitutional isomers. So we formed one chloropropane and two chloropropane in a 1-to-1 ratio. Some of you may be like, okay, like why is that significant? Well, if we look at the number of hydrogens, let's say in blue in this case, and the number of hydrogens in pink, we have a 6-to-2 ratio, right? Or a 3-to-1 ratio. And so that's actually the ratio that we might expect, provided each of those hydrogens is equally reactive, right? So we would expect a 3-to-1 product ratio. But that's not what we get. We get a 1-to-1 ratio. And so why is this the case? Well, we already introduced the stability of the radicals and the strengths of the bonds. And so let's just remind ourselves of that again. So we have our methyl, we have our primary, we have our secondary, and we have our tertiary alkanes, right? So I'm emphasizing these CH bonds because that's really all we care about, right? So there's the methyl, primary, secondary, and tertiary. And then I'll highlight in red again those CHs just so we know what we're focusing on. And then as we go from left to right, we have obviously an increasing number of R groups, right? But then we also have an increased ease of hydrogen abstraction. And that means that is going to be a weaker bond. We can also see that in our bond dissociation energies chart. I'll hook you up. Don't worry. I'll feed you, baby bird. 435, 410, 397, as well as 381 kilojoules per mole for that tertiary. So we can see that obvious trend, those are values that have been obtained already. We didn't make those up. And then what we can conclude, therefore, is as we go from right to left, we have an increase in bond strength, right? Okay, so let's take a look at the bromine, halogenation of propane, right? So we got elemental bromine in the presence of heat or light and propane. We're still going to get two products, right? We get one bromopropane and two bromopropane. But we got one on the left, right? So, sorry, let me switch it up. So we got one on the left, right? One bromopropane, but 99 on the right. So that means we're forming 99 two bromopropanes for every one bromopropane. Say what? What you talking about, Jess? What is this guy even talking about? Well, that's what's super cool about bromine, right? Without even knowing really, like you're not super into synthetic chemistry, but you can think that like, okay, well, if you form 99-to-1 ratio, that's obviously better than a 1-to-1 ratio, right? Because we have a mixture of products for the chlorination. Sorry, I forgot to put actual and expected on that ratio. And 99-to-1 is way better because it's very selective, right? And so chlorination is fast, but it's unselective. And then bromination is going to be slower, but it's selective. So you're forming majority one product, if not all one product, but you're also saving money as well, right? So you're not wasting propane molecules to make some other undesired bromine compound, but you're also not having to purify as much. And so there's a variety of reasons why selective reactions are much better, okay? So the major product is going to be the result of a cleavage of the weakest CH. That's why we see that secondary CH is 397 kilojoules per mole, which is 13 kilojoules per mole lower than the primary, right? So that's obviously going to be better. And so this makes bromination more synthetically useful, okay? So if you have the chance, do bromination, okay? So what time is it then? Practice. You want to talk about practice? Let's do it. So what we're going to do is just draw some products or starting materials, and we're going to go do a bromination. And so I want you to tell me basically what is the major product. Okay, so basically all we're looking for is where is the weakest CH. Okay, and the weakest CH is a tertiary, and then it's a secondary, and then it's a primary. Okay, so basically we're always going to look for a tertiary. Unless we don't have one, then we move on to secondary. All right, that's the easiest way to do it. And so pause the video, try it on your own, and then see if they match up with mine. Boom, there's the tertiary bromine right there. This one's a little bit crazier, right? So you have to pay attention. Notice that there's no hydrogen on that highly substituted position. I put the emphasis on there, weird. But there is a hydrogen at this position, highlighted in red. Hopefully you can see that. That is a tertiary position. The other one is a quaternary position, so there's no hydrogen. Okay. Now this one right here, we got an easy tertiary bromine right there. So the tricky ones are the ones that are quaternary. So just make sure you're keeping an eye out and not making silly mistakes and thinking that the bromine can go on that carbon, because then you'd have 5 bonds, and you don't want to do that. Okay, so yeah, the secondary position is weaker CH than the primary, but why don't we get the same outcome for the chlorination that we do for the bromination? So here's our explanation. We already seen these numbers in the previous video. So this is using the explanation for the halogenation of ethane, right? So we have the generic scheme up above, and I want to remind you that I kind of broke these down into 2 steps. So the first step in blue below is hydrogen abstraction of ethane, and then that forms an HX, so HCl or HBr. Okay, so those are the 2 values that are there. And that resulted in these 2 different curves. And after that hydrogen abstraction, we had an ethane radical, right? And so that's what that intermediate is, the trough in the graph. And then for bromination, it was an endothermic process. And then for chlorination, it was an exothermic process, right? And so looking at step 2, we have, for step 2, let's see, what was that? That was the formation of the, I'll put X ethane, so it's the haloethane or bromoethane or chloroethane, right? And then we also formed the X radical, which was, because this is the propagation step, it's going to allow it to go back, react with another ethane, right? And so basically the far right is the product, bromoethane and chloroethane, right? And so again, this is the propagation step, and I'm pointing these out because I want you to notice the difference in the curves, right? For chlorine, they're both exothermic. For bromine, the first step is endothermic and the second step is exothermic. Okay, so recall the Hammond Postulate, right? And so the Hammond Postulate tells us that for an endothermic reaction or process, the transition state resembles the products. Okay, so transition state in an endo reaction, I always write represents, resembles the products. Okay, so why is that important, right? So if we take a look at this bromination process, we can see that first step is an endothermic process. And so the formation of that ethane radical is endothermic, and the energy of that transition state in that first step is going to be more or less dependent on the stability of that radical. Okay. Now, the transition state in an exothermic reaction resembles the reactants. Okay, so what does that apply to? Well, that's going to apply to the chlorination process. So you can see that first step is exothermic, and that means that the transition state is going to resemble the reactants. Okay, so the stability of the radical does not come into play here. Okay, so again, I want to point out the first step is a rate determining step, right? And so that's important. So this is the answer to our original question. Why does bromine make selectively 2-bromopropane over chlorine, which makes 1-to-1 ratio of 1 chloropropane and 2 chloropropane? Okay, so bromination, I got two curves here for you. For that first step, we're focusing on that rate determining step only because that's going to determine the reaction rate and products, right? So we've got our secondary radical, which is more stable than our primary radical. And this is just because the secondary has more R groups, right? It can donate into that electron deficient carbon radical. And so it's the same thing as like a carbocation, right? And so this is going to lower the activation energy and going to give you faster reactions and a single major product or majority product. All right. We might say that's legendary. You know what I mean? Anybody down with How I Met Your Mother? Anyway, so let's take a look at the chlorination. So how does chlorination differ in terms of this first step and the reaction? Energy associated with the transition state and the products, yada yada. Well, since this is an exothermic reaction, we have obviously different energies for the stability of those final product radicals. But the starting energy is the same because it's the reactants, and the transition state energy is roughly the same as well because it's an exothermic process and it resembles the starting materials, right? The reactants. And so roughly equivalent in energy. Okay, so that means if you have a more stable radical, it does not affect the stability of that transition state. And so that doesn't really do anything for us, right? And so since the transition state resembles the reactants and is equal in energy for either process, that means statistically we can form either product, right? And that's why you can get either radical, which means you're going to get either chlorination product, which means that you're going to get a mixture and you're going to be mad. And it also means that chlorination is lame. Okay, so it is what it is. What are you going to do about it? All right, I got to make sure I write this really important note. Lame. Okay, lame. And that's chlorination for you. Okay. Oh, I just noticed when looking at this faster reaction, I wrote faster reaction and I meant the major products forms faster than the minor product, right? And that's not faster than the chlorination because the chlorination reaction does occur much faster. Okay. And chlorination is lame. Just keeping with the theme of How I Met Your Mother. That's the face I make when I have to do a chlorination. Grr, arg. All right, so just real quick, halogenation is basically making lame alkanes synthetically useful because remember, like last semester, all we did was we started to move into a lot of synthesis problems, and we always started with something that wasn't an alkane because alkanes are essentially non-reactive, right? And so, as far as we were concerned last semester, but now we got something. Okay, halogenation can make them useful now because it makes them into haloalkanes, and we can make all kinds of stuff from there. Okay, also, Br2 is better than Cl2. Okay, bye.